Okay, we can start the lecture now. Last time I gave the definition of L2 Betti numbers. They are associated. So the usual Betti number is associated to a cell complex or to a topological space. In the case of L2 Betti numbers, we have not only a complex but also a group action on it. So the group is important. So this L2 Betti number is defined in terms of for a complex but relative to some group, with respect to some group. We usually assume that there is some action of gamma on, say, y hat. This can be generalized. There are more general versions of this. One can actually define L2 Betti numbers for arbitrary actions on arbitrary topological spaces. So there are ways to do this. There are results by Luke which generalize this notion. So there is a more general setting for this. But for our purpose, we consider only cell complexes and free actions by a group. So for a free action. And let's just consider some examples. We did consider some examples last time, right? One example was the finite tree. I mean, we talked about the usual Betti numbers, not L2 Betti numbers. And another example was like this infinite line. We also computed L2 Betti numbers for that. So the following statement is a generalization of that. So the following lemma says that if y hat is a forest and we have an action, y hat is a free action, free and co-compact action on this forest, then I need a notation here, and y we denote y to be the quotient. So we take y hat and take the quotient by this action. So we consider the set of all orbits. Say one agent here is an orbit in y hat. One vertex here is an orbit of vertices in y hat. If we denote the quotient y, then on one hand we can talk, since we have this action, we can talk about L2 Betti numbers. And I'm going to take the first L2 Betti number, B1, 2 of y hat gamma, right? So you remember it's defined, you take the L2 homology of this in dimension 1, and then you consider this L2 homology as a gamma module, as a Hilbert gamma module. And then for such, there is a notion of dimension. So that's the dimension that we take. This completely kind of formal, abstract notion of dimension turns out to be equal to the reduced rank of the quotient. This is the reduced rank that we saw quite a few times before. This is the same as the cardinality of the maximal essential set, right? It's the number that we defined as maximum of 0 and what? Negative Euler characteristic and negative Euler characteristic, so of two numbers. Turns out that this number is equal to the L2 Betti number. It has this nice analytic description. So this is why it is conceptual, right? This is actually a concept, right? It's not from the definition of this, like taking maximum of 0 and something else. It doesn't seem like anything conceptual, but when you see this equality, then this is a concept now. So let's prove this. Proof. So what's the picture? We have maybe. So here is the picture. I'm picturing y hat here. Y hat, and then you have the quotient. Then you have some graph. This is the graph y, right? This is not the most general picture. It might happen actually. So what I drew here, it's an orbit of components. And the group gamma permutes those components. We have an action. But the quotient of each of those components, so you can take the quotient of the whole thing by the group gamma. Or you could take the quotient of just one component by the stabilizer of that component. It's the same thing. It would be the same quotient. But this is not the most general picture. The most general picture would be you might have something else. Maybe you have some more. And then you might have another component. This y doesn't have to be connected, right, in general. So in other words, you might have several orbits of components in y hat. And each orbit of components will give rise to a component in a quotient. So the first observation is that we can assume that y hat is connected. So first we want to reduce this general situation to the case when y hat is connected. So why is this? So first know that the L2 number and the reduced trunk are additive under disjoint unions. By which I mean, if you take, this is one orbit of components, this is another orbit of components. If you know the L2 number just for this part, and if you know the L2 number just for this part, then the L2 number of the whole thing will be the sum of them. It is additive undertaking such orbits, undertaking disjoint union of such orbits. The same thing here. If you know the reduced trunk for this component and you know the reduced trunk for this component, then the reduced trunk of the whole thing, by definition, is the sum. This is how we defined R bar. So it is additive. So we can assume. Assume that gamma acts transitively on components, on the components of y hat, right? That is one reduction. So in other words, there is only one orbit of components. But then, as I mentioned before, instead of considering the action, the gamma action on this whole orbit, we can consider only the stabilizer. So pick a component of y hat and consider the stabilizer. Consider its stabilizer. The quotient of the whole y hat. So I'm considering this case now when y hat is this. The quotient of the whole thing by gamma is the same thing as the quotient of just one component by the stabilizer. So what we are going to do, we just replace. Instead of y hat, consider one component. And instead of the group, consider the stabilizer. So we can assume that y hat is connected, and yeah, I guess this is all. So and gamma acts on this connected graph now. So we replace gamma with the stabilizer. So from now on, y hat is connected, and we still have this action of gamma on this, and the quotient is some finite graph. Okay, so since y is connected, so we started with a forest. But now if we, so what is a forest? A forest is this disjoint union of trees. Since now y hat is a connected forest, that means it is a tree. So y hat is a tree. And we have gamma acting on y hat So gamma acts on a tree freely. It's a free action. That means that so gamma is the same thing as the fundamental group of what? Of the quotient. It's a connected tree. It's a tree, so it's connected. We take the quotient. So this is pi1 of y. Right? Gamma is the fundamental group because it acts freely on a simply connected space. It's a general fact that if a group acts on a simply connected space freely, then that group is the same thing as the fundamental group of the quotient. So gamma is this. So gamma is a free group. From the beginning, gamma didn't have to be a free group, actually, right? It could be any group pretty much. But now, since it acts freely on a tree, it must be free. So it's a free group. And now we need to consider cases. So case 1, y hat is finite. If it's a finite, so it's a tree and it's finite. Then we compute the first L2 Betty number of y hat with respect to gamma. So what is gamma? Since gamma acts freely on a finite tree, it must be that, so it implies that gamma is the fundamental group of the quotient. But then the quotient, so the point is that it must be the identity. Then gamma is just the trivial group. This is the only case that's possible. The only free action on a finite tree is the action by the trivial group. Since gamma is trivial, so what is this then? Y hat is a finite tree. Gamma is the trivial group. This means that when we compute l2-Homology, l2-Homology of a finite complex is the same thing as just the usual homology with complex coefficients. And gamma is the trivial group. So when we take the dimension of over the trivial group is just the usual notion of dimension of vector spaces. That means that we obtain the usual Betty number of y hat. But what is the usual Betty number of y hat? This is the example that we did last time, right? What's the answer? What's the first Betty number of a finite tree? What's that? Yeah, okay. What's the Euler characteristic of a tree? 1. So number of components minus 1 times number of components. That is 0. So yeah, it was a correct answer, but it happens to be 0 as well, right? So yeah, so we computed this. This number is 0, but 0, of course, happens to be equal to the reduced rank of y. Maybe I should say just let's see. This is the same as just y. Y is equal to y hat here. It's the same thing. Y was the quotient of this by the trivial group. So it's the same thing here. So 0 is the reduced rank of a tree. We know that, right? The reduced rank of any finite tree is 0. So in this case, we prove the equality. Case 2 is that y hat is infinite. So it's a tree, but it's an infinite tree. We want to compute the first L2 Betty number for the action of gamma on y hat. We just use the definition. it's the dimension of the first homology. The first homology is obtained by taking the first L2 summable chains of y hat, and then the 0th L2 summable chains of y hat. And then, since this is a graph, there is nothing in dimension 2. Dimension 2 is 0. The L2, the Betti number in dimension 1, is the dimension of homology, of the L2 homology. But what's the homology? Since there is nothing coming from here, 0. The homology is the same as the kernel. The first homology of y hat is the same as the kernel of this D1 of the boundary map. And we want to find the L2 Betti number is the dimension of this homology. So we want to find the dimension of the kernel. But what's the dimension of the kernel? It's the dimension of the whole thing minus the dimension of the image. We can use additivity. So I'm using additivity property, you remember, for short exact sequences. So we only we want to find the image of this map. What is the image? We did this last time. So we claim that D1 is weakly surjective. And that means that the closure of the image is this whole space. So i.e. C02 of y hat is equal to the closure of the image of D1. That's the claim. How do you prove this? We did this last time again. And in those handouts that I gave, there is also a proof of this. It's a similar fact, which I will state just in a moment. But you remember, we took any element in here. Any element in here is a linear combination of vertices. Infinite linear combination. So just take one vertex. And we want to approximate just that one vertex by some images of this. So we did this last time. So the proof is by, so any vertex V in y hat can be approximated by boundaries of one chains. So we did this. That means that this map is weakly surjective. So if you consider this sequence, so how do you find the kernel? There is a corresponding weakly exact sequence, the kernel of D1, then it injects into C1 to y hat, and this is weakly surject. This is a weak surjection onto C0 to y hat, and since this is weakly surjective, then this becomes a weakly short exact sequence, right? What we want to find the dimension of the kernel. So the dimension, the first L2 Betti number of y hat gamma is the same as the dimension of homology once again, but that's the same thing as dimension of the kernel D1 over gamma. And now what's the dimension of the kernel? You use this weakly short exact sequence. That is the same as the dimension of over gamma of C1 to y hat minus the dimension of C0 to y hat. Okay, what is this? We consider this is L2 of the edges on the edges, and this is L2 on the vertices. But what's the set of edges? The set of edges is split into orbits. And so this is the dimension of L2 over sigma 1 of y hat. This is the number of edges. I mean the set of edges, and this L2 on that set minus the dimension over gamma of L2 of sigma y hat 0. This is the dimension of the on the space on the vertices. But this set is a copy. It's gamma cross some finite set. And what's that finite set? So in other words, it's this is several copies of L2 of gamma. And the question is how many copies? As many copies as you have orbits, gamma orbits in here. The same thing here. This is a copy of L2 of gamma cross some finite set. What is that finite set? It's the number of orbits of vertices. So it's the number of gamma orbits of edges in y hat. Maybe I should write it like this: minus the number of gamma orbits of vertices in y hat. Okay, but that's the same thing as the cardinality of edges in the quotient. So y is the quotient of y hat, and E of y is the number of edges, is the set of edges in y. So we take that number minus the number of vertices in the quotient y. Similarly here. But what is this number? We have a finite graph y, and we take the number of edges minus the set of vertices. That is negative Euler characteristic of y. Right? Okay. But this is the same as, so I claim now that this is the same as the reduced rank of y. Why is this? This is because, what's the reduced rank? Once again, it's the maximum between of two numbers, 0 and the negative Euler characteristic. All we want to show is that this number is at least 0. Then we are done. And this number is at least 0 because y is not a tree. Is not a tree. If it was a tree, then y hat would be the tree itself. Y hat is a connected tree whose quotient is y. So if y was a tree, then it means y hat, this y hat must be that tree, and gamma must be the trivial group, and that would be case 1. It's not the case here. So y is not a tree, so that means that the negative Euler characteristic of y is at least 0. Since it is at least 0, then the negative Euler characteristic is the same as the reduced rank. That proves the statement, right? So it gives the analytic description of the first L2 beta number for finite graphs. But that gives us a hint. Now we can write everything that we've done so far in analytic terms. So what is the Hanna-Neumann conjecture?
You really need co-compact action?
No, it can be defined, but it doesn't make much difference between like co-compact and non-co-compact, because you would have to consider the case when something is infinite, and you will always have this trivial case when something is infinite. You don't really have to have co-compact actions to define things. Yeah. So the strengthened Hanna-Neumann conjecture. It can be stated as follows. You have this situation. So you construct a system of graphs as before. So you start with a group, 2 subgroups in it. That group is free, 2 subgroups in a free group, and then you construct the corresponding system of graphs. In the corresponding system of graphs, you have those forests, x hat, y hat, z hat, s hat, and you have the group action on them in those. The statement of the Hahn-Neumann conjecture now can be restated as, instead of reduced rank, you replace everything by in every place you replace the reduced rank by the first L2 number. The first L2 number of S hat, gamma is at most B1 of 2 of Y hat gamma times B1 of Z hat gamma. So this is the restatement. Once you state it in this form, then you immediately see how you can generalize the question. So a more general. Ask the submultiplicativity question. Given a system of complexes, under what conditions do we have B? Now we can take arbitrary dimension I. It doesn't have to be 1. The ith L2 number is at most the ith L2 number of y hat gamma and the ith L2 number of z hat question mark. Let me note also that even in the case of graphs, this restatement actually is more general than the original Hahn-Neumann conjecture. Why? Because in here, those graphs that come out in the statement of the strengthened Hahn-Neumann conjecture, those graphs are forests. But we can actually ask the same question in a case when these are not necessarily forests, but just arbitrary graphs. Is that true or not? And the answer is yes, it is true. Once you restate it in this form, this is true now, not only for forests, but for arbitrary graphs, whenever you have a free action of gamma on the graphs. So this holds more generally for graphs y hat, z hat, s hat. Not necessarily forests, arbitrary graphs. And how do you prove this? The proof is pretty much the same as what we did. You prove the deep fall property. So use the deep fall property. Property for graphs. You remember why we needed this. So first you prove deep fall property. We did this. I proved it not only for forests but for arbitrary graphs. And then this deep fall property implies that certain set of edges is essential. Then we needed to prove maximality. We needed to prove that that set of edges is actually maximal essential. And to prove maximality, actually one can use an analytic argument. And that analytic argument is very general again. It holds not only for graphs but for complexes or just completely, purely abstractly. It always holds. So one can do this. But let's do it step by step. So let's try to restate everything that we've done so far in these analytic terms. Yeah.
So you still assuming gamma is free group?
No. Yeah, just arbitrary group. This is a very general question. But the definition of deep hole property, remember, in the definition, we use the fact that gamma is left orderable. Or at least, I mean, you can relax this slightly. We use the fact that there is an order on a set of edges, such that it's preserved under the group action. So you don't really need to use the fact that the group is left orderable, but rather there should exist an order on the set of edges, which is invariant under the group action. Yeah, so in the definition here we used left orderability. In this very general statement you don't even need to assume, but it might be false in general, who knows, but I don't expect it to always hold. But it's an interesting question, when it holds and when it doesn't.
So system means you have the pullback system?
Yeah, it's this right here, this one.
Okay.
This is the system of complexes, yeah. Yeah, so the forest, why did we need the notion of forest? Why was it, we only needed forests to translate, to prove this lemma that I started with today. In order to show that the L2 beta number is the same as the reduced rank, this is where you need the assumption that the graph is actually a forest. But if you don't deal with the reduced rank at all, then we can just forget about the reduced rank, right, and just work with the L2 beta number. Then you do not need this assumption. So we only needed forests to relate the L2 beta number to the reduced rank. If we work directly with the L2 beta number, we don't need forests. It can be for graphs. Then this statement is true, and generally for complexes, one can ask this question. It's an interesting question. So once again, remember how we proved this for graphs? We use the deep hole property. And the point is that for graphs, the deep hole property always holds. We proved this. For complexes, we don't know. And I kind of suspect that probably not. It probably does not hold in general. But there are probably many examples when this deep hole property holds. If it does, this general submultiplicativity pretty much can be shown. So the point is that submultiplicativity, it's not a precise statement, but kind of roughly corresponds to the deep hole property in certain dimension. But first I need to say what deep hole property means in this setting. So let's go through the list, and maybe just one more remark. Another version of this submultiplicativity question is you replace B by A. So what is A? What is this BI? It's the dimension of the ith homology. The homology is the dimension of what? Of the kernel divided by the closure of the image. Now I suggest we take not this quotient, not kernel divided by the image, but just the kernel. So let AI be let's see, of y hat gamma be the dimension of gamma of the kernel of the boundary map in dimension I. So if we dealt with graphs, and so for graphs and if you take I to be 1, then the homology is the same as the kernel. there is no difference between A and B. So A1 of y hat gamma is the same as B1 of y hat gamma. The difference comes when you actually have, say, two-dimensional cells. It's a two-dimensional complex, then it might be different. So one can ask the A submultiplicativity question. So the A submultiplicativity. Again, the same question. Under what conditions on a system of complexes AI to y hat, the same thing, just replace B with A. S, the gamma is at most AI y hat gamma, AI z hat gamma. Question mark. And this question seems to be, it might be even more natural. That is interesting still. But this question might be actually even more natural because we will see, because it relates to the Atiyah conjecture in analysis. This has a more direct relation to it. So, but we will see this later on. Let's now take some notions that we already considered and see how they translate in these analytic terms. So the fall. You remember, you have a complex, or rather just a graph in that example, but I want to generalize this to complexes later on. The fall, you take y hat to be a graph, then you take sigma be an edge in y hat, and E is a set of edges in y hat, which is disjoint from sigma. What does it mean for sigma? So if sigma falls into E, what does that mean? So let's recall the definition. It means that one of the two conditions are satisfied. Either the picture is like this. This is sigma, and this blue is in the relative graph. So we consider the graph generated by this set E. So this in the relative graph. It's a component of the relative graph y hat of E. Right. So y hat of E is just what? All the vertices are the same as in y hat, but the edges are only those which are in E. So we restrict the number of edges only to E, but keep the same vertices. In this relative graph, we can take a component. So let's call it a relative component. So it's a component relative to this subset of edges. Or we have this picture. So this is sigma, and then we have two infinite. So either the two components coincide. They might be finite or infinite, it doesn't matter, but they coincide. Or the two relative components, so the component containing the first vertex and the component containing the second vertex, are both infinite. Disjoint, and again they might both infinite. We allow them to coincide.
Is it a definition of one?
Of what?
Is it a definition of one?
Yeah, this is what it means for sigma to fall, for an edge. That's what we did. Sigma falls. But now, how would you describe this in analytic terms? It means that if we take the boundary of sigma, so we claim that this implies if one of these conditions holds, if sigma holds, then what can we say about the boundary of sigma? The homological boundary, it's the difference of these two vertices incident to sigma. But this difference of two vertices is actually also a boundary of some of a finite vein here. But that finite vein is completely in this blue, in the component of the relative graph. Okay, or what happens in this case? Take this just one vertex. In this component, I can consider bigger and bigger subsets. Call it Wn. So where n is, for any number n, we can pick a number, pick a set whose cardinality is n, a set of vertices, and then we can connect sigma by a path like this, and we can run the same argument as before to show that this sigma minus, let's call it sigma. Sigma minus is the initial vertex of sigma, and this is sigma plus, the terminal vertex. We can show that sigma minus can be approximated by boundaries of one-dimensional chains. Those chains are linear combinations of paths. You take n paths and then divide by n. You take the average over those paths. The boundary of that path would be the linear combination of the initial vertices of those paths and sigma minus. But that part becomes arbitrarily small in L2 norm. We did this before. Right? You can take a look at these notes that I handed out. That means that sigma minus can be approximated by boundaries. The same you can do for sigma plus. It can also be approximated by boundaries. So the difference of those can be also approximated by boundaries of one-dimensional chains. That, in either case, what you get is that the boundary of sigma lies in the closure of L2 of the boundary of L2 of E. Consider all L2 summable chains on that set edges, not on all edges, but only on this part. And then consider all boundaries, the boundaries of all those. If we take the closure, then the boundary of sigma lies in a closure. The boundary of sigma can be approximated by boundaries of one-dimensional chains which are supported in E. Okay, what if it doesn't fall? Then what happens? If sigma does not fall into E, what do we have? It means the opposite of this situation. It means that the components, consider the components, the relative components containing the initial point and the relative component containing the terminal point. Those two components do not coincide. They must be different. That's one assumption. And at the same time, they are not both infinite. So that means that one of them, at least one of them, must be finite. So the picture is like this. Sigma is here. And either these two components are like this. These are finite components. Or sigma, or one of them is finite, but another is infinite. Right? That is the situation. In this case, we claim that then the boundary of sigma does not belong to the boundaries of L2 of E. So how do we check this? So take the boundary of sigma. Say in this case, take the boundary of sigma. It's the difference of sigma plus minus sigma minus. If there is some one-dimensional chain, linear combination of edges, whose boundary is this, but these two components are completely disjoint, that means that sigma minus must be the boundary of something. The boundary of something supported here. And sigma plus also must be the boundary of something, of some one-dimensional chain supported here. Since the two components are separate, it means that that should hold separately. Not only the whole boundary should not. So if the boundary is a boundary of something blue, then each of these points must be the boundary of something blue. But now you check that whatever linear combination you take, you take some edges here. No matter what linear combination of edges you pick, this will never be. So for any, if say x is a one chain in a finite graph, then the boundary of x cannot be a vertex, just one vertex. You cannot obtain the boundary being the vertex. So what's the reason? The reason is that there is something called the augmentation map. You take what's the augmentation? You take a zero-dimensional chain. So start with any one-dimensional chain. Take the boundary. The boundary of this is a one-dimensional chain. And what can we say about? So what's the augmentation? You just take the sum of all coefficients. This is a linear combination of vertices. You take the sum of all coefficients. What can you say about the augmentation of this? So C naught of some, let's call it K. K is some graph. Two just complex numbers. The augmentation map. So what is epsilon of the boundary of x? If x happens to be just one edge, what's the augmentation of the boundary of the edge? If x is just one edge, you take the it's an oriented edge, so you take the difference of these two vertices. So the difference means that this comes with -1 and this comes with +1. What's the augmentation? It's +1 minus 1. You take the sum of the coefficients. It is 0. Then if x is, then by linearity you extend it to any linear combination of edges. So this is 0. So the augmentation of the boundary is always of the boundary of something finite. This is a finite chain on a finite graph. Finite linear combination. So it cannot be a vertex because the augmentation of, say, if I take the vertex sigma minus, the augmentation of this is of course 1. It's the linear combination of just one vertex and 0 coefficients everywhere else. They are not the same, so that's why that dx cannot be sigma minus. Yeah, and I guess I should say that if you can approximate something by a finite chain, if everything happens just in a finite set, then approximation, we can remove this from here, the closure. If you can approximate, then you can actually realize it as a boundary. Because we are talking about finite dimensional vector spaces. In a finite dimensional Hilbert space, closure, you don't need to take closures. They are all closed already. Okay, so this shows that this property is equivalent to the statement that sigma does not fall. So i.e. we proved that for finite for graphs. For graphs, sigma falls into E if and only if the boundary of sigma belongs to the closure of L2 of E. It's an analytic restatement of the fall, right? Once you restate in these analytic terms, again, you immediately see that the same, you can just take this as the definition of the fall. And then it implies not only for graphs, but for complexes. You can apply this to any dimension in any complex.
So
Yeah.
Don't you need to consider the case that sigma minus and sigma plus are both in one infinite component?
No, so sigma falls into E. This is a notation, right? Sigma falls into E. That means that it means that sigma. It means that the two components coincide, or both components are infinite.
That coinciding components can be infinite?
Yeah. This means, this condition says that they coincide, no matter if they're infinite or finite. Yeah. So the opposite of this says that the two components must be distinct, disjoint. Yeah. So given a complex y hat, if you take sigma in sigma I of y hat. So sigma now is an I-dimensional cell in y hat. And given E, which is a subset again of sigma I of y hat. E is now a subset of I-dimensional cells. Say that sigma falls into E. Yeah, and I assume they are disjoint. So this is minus sigma. Say that sigma falls into E if the right sigma falls into E. This is the notation. If the boundary of sigma is in the boundary of L2 of E. Exactly the same statement, but now, of course, E now is a set of I-dimensional cells, and this boundary now is the boundary in dimension I. It's a higher dimensional analog of this. Then, additionally, we assume that there is an ordering. So if there is an ordering on the set of I-dimensional simplices, I-dimensional cells of y hat, we can define what it means for sigma to be order essential. Say that sigma is order essential if sigma falls into what? Into the set of all I-dimensional cells that are smaller than sigma with respect to the order. We had this notation. Sigma I of y hat that are less than sigma. It's the set of all I-dimensional cells that are less than sigma. And you require sigma to fall into it. So i.e., let's write it again. It means that the boundary of sigma belongs to the closure of the boundary of L2 of this set. So that means, informally speaking, say, let's draw a picture for dimension 2. So sigma now is like a two-dimensional cell. say, think of dimension 2. Then for sigma to fall into some set E of two-dimensional cells, it means that you can complete it with something two-dimensional, some kind of picture like that, in such a way so that the boundary of this blue thing is almost the same as the boundary of sigma. You can approximate the boundary of sigma by the boundaries of the like two-dimensional chains in this case, which consists of elements of E, which are completely in E. So this is in E. So in other words, sigma is order essential if you can complete it to almost a cycle using the cells in this set. If it's a finite complex, then that should be reasonably clear that you can. So what should be clear? If it's a finite complex, then you can remove this closure here. Then this is equivalent to saying that you can exactly complete it to a cycle, if y hat happens to be a finite complex. But in general, who knows? It's an interesting question. I mean, of course, it's either order essential or it's not. But the next property that I would like to generalize, to rewrite in this analytic language, is the deep fall property. And that one is not clear in general. So the deep fall property property for the action of gamma. Or actually, I don't need an action. So all I need is the just an ordering. Maybe I should write just an ordered for a complex with an ordering, with an order complex, let's call it y hat, with an order on total order on the set of I-dimensional cells. This deep fall property says the following. So if for any sigma in sigma I y hat, and for the following should hold. If sigma falls into the set of I-dimensional cells less than sigma, right? This is equivalent to saying that sigma is order essential. Then sigma also falls into, so what's the statement? It's completely analogous to what we did for graphs. Then it must also fall into the set of order inessential cells, and I should have defined it, I guess, earlier. But, the inessential are denoted by I y hat less than sigma. So here, this is the set of all order inessential cells. Let me write the definition. Is the set of all order essential I-dimensional cells in y hat, and the I sub I y hat, it's the complement. It's the set of all order inessential. Order inessential. So the deep fall property says that it might hold or not, but it's just the definition of that property. It says that if sigma falls into all the cells that are smaller, then it also falls into a smaller set only those cells that are order in essential and are smaller than sigma. And in general, I don't really know the answer, but in general it looks like it's probably there might be some counterexample to this property in general. So we are interested, of course, in a situation when y hat is some complex and then some group gamma acts on this complex. We assume that gamma is, say, gamma is left orderable, and then that induces an ordering on a set of I-dimensional cells. So that would be an interesting case to consider. So the deep-fall property, in other words, can be stated for actions. It's a question about actions. That's the framework in which it is interesting. So the deep-fall property is a question about actions. Of left orderable groups. So it's a question about actions. It's not a question about the group, it's not a question about the complex really, but we are interested in both when we have a complex and a group. Why is this interesting? Because it implies submultiplicativity. Yeah?
Can we claim that the default property is always the case for trees?
For trees, when I is equal to what?
I equal to
1. That's what we proved. The deep-fall property holds not only for trees, but for any graphs. And we pretty much provided the argument.
I have a question.
Yeah.
Should gamma act transitively on I cells?
No, it doesn't have to be transitive.
Then can you define the order on I cells?
Yeah, we can, as we did. So we identify when the group gamma acts on y hat, then there is an induced action of gamma on the set of I-dimensional cells. Right? It permutes the cells. We did this for graphs. When this is a graph, this is I here. When this is graph, we consider the set of edges in y hat. And then sigma I can be, we assume that, yeah, again, I'm assuming that the action is free. Maybe if that was your question. So I'm assuming the actions are free. It's an interesting question in general, but let's stick with free actions. So if the action is free, then I-dimensional cells can be identified with gamma across some finite set. And co-compact. Yeah, I guess I don't really need to assume co-compact or anything, just any set. So some set, A set. So this is the set of orbits, or you can view this. You consider all the orbits in this set. Each orbit is a copy of the group. And this set just corresponds to one orbit. Or more conceptual way, maybe, this set corresponds to picking one representative in each orbit. Fundamental domain.
This I cell with that dipole property, if you don't assume compact action, then after moving out, I mean, it doesn't do any, can be, it's not a cycling, it cannot be.
You don't mode out.
Then, I mean, where do you use I cell with the full property?
So in the case of graphs, we use the deep-fall property to prove that certain set is maximal essential. The certain set is essential.
Right.
Set of edges.
So it should contribute to the homology after moving out.
Not really. That's the. it's the difference between usual homology and so. If you have a group action on some complex y hat, you can talk about two things. First, so assume, say, co-compact free action. Then denote y the quotient. One can talk about two things. One thing is the l2-Homology. L2-Homology, I-dimensional, of y hat. And then consider the induced group action on this. This becomes a module, so we can talk about the dimension, which is L2 Betti number. The second thing is the usual homology of the quotient. And this can be, say, a finite graph, right? The point is that there is not much relation between the two. They are completely different. So this quotienting, that's why it's a good idea instead of y to consider y hat, because it gives you some more information about y that you couldn't see from the complex itself. But when you took like the universal covering, then it gives you more information.
So the I cell with let's say full property, they fall into something that contribute to then this L2 homology.
First of all, deep fall property is not a property of a cell. It means that it's for any here. It's a property of the whole action.
Right. So this is a set of I cell. I mean, sigma I is a set of is a chain or
sigma I is the set of all I-dimensional cells. Yeah, it's a property of cells. It's a property of all cells together.
So maybe I don't understand the motivation why you think this kind of cells with a default property. I mean, what's the motivation?
So there are two motivations. First is that this deep fall property was used in a proof of the Hahn-Neumann conjecture. That's one motivation. The other motivation is that when you took this deep fall property and restated in these analytic terms, it is going to be related to the ATIA problem, which is a problem in analysis. So there are two things to which this deep fall property relates. It relates to both things. So kind of intuitively, this deep fall property roughly corresponds to the ATIA problem, which I will talk about later on. So that's the second motivation. And the third motivation is just generally, if you start with a finite complex y, and then you can take, say, the universal covering, take y hat to be the universal covering of this. Then if you can say something about the homology, then it tells you something about the original complex. So that's the philosophy. It tells you it gives you some more information about y that you didn't see just from y. But when you took the universal covering, it somehow, it gives you more information. So maybe I should say, one relation between the two. There is actually a very nice, it's not the case that the homologies correspond, right? Say if this is a connected finite complex, what's the zeroth homology? The zeroth homology would be just C, the complex, the one-dimensional vector space. But what's the zeroth homology of this? If we took y hat to be connected and infinite, if it happens that the universal covering of y, for example, is infinite, then we proved today that the zeroth L2 Betti number is going to be 0. We proved it last time, right, for that example, but exactly the same holds for any infinite graph. So maybe I should state this too. If y hat is an infinite graph, then and gamma acts on y hat, again with the same assumption, freely, co-compactly, then the first, let's see, the zeroth L2 Betti number of y hat gamma is 0. How do you prove this? In the same way. you approximate any zero-dimensional chain by boundaries. It's possible to do. So it follows from the fact that any vertex in this graph can be approximated by boundaries of finite one-dimensional chains. But that shows that in dimension 0 there is no relation between this and this. Those numbers, the the zeros Betti number for the quotient might be completely different from the zeroth dimension number from for y hat. Nevertheless, it's possible to show that a certain combination of Betti numbers is equal to a certain combination of L2 Betti numbers. What's that combination? It's the alternating sum. Also known as the Euler characteristic of the space. So, if, again, in the same situation, so also, again, if gamma acts on y hat, and y hat is a complex, again, assuming free co-compact, then so let's try this in the middle. And again, the quotient. So y is the quotient. Then the Euler characteristic of the quotient can be written in two different ways, but it's the same number. One is the classical homological definition of Euler characteristic. This is the alternating sum of the usual Betti numbers. The alternating bi. I goes from 1 to infinity. Right. I'm assuming it's a finite complex, of course, so the sum is actually finite. And this is the alternating sum to infinity of the I of bi2 of y hat gamma. And bi, maybe I should say, yeah, bi of y here. These are the L2 Betti numbers of y. These are the usual Betti numbers of y. These are the L2 Betti numbers of y hat with respect to gamma. They happen to be, yeah.
You see, this starts from 0 or 1?
Oh, yeah, sorry. Yeah, 0. So these numbers happen to be the same. How do you prove this? So maybe I should leave it as an exercise. Prove this equality first. And once you saw this equality, then you know how to prove this one. You exactly repeat the argument one by one. So it does not mean that, say, B naught here is equal to B naught here. They are not the same. They are different. But this alternating sum happens to be the same as this alternating sum. So do this as an exercise. Prove this equality. If you don't know how, just open any book in algebraic topology. Do this. And then just look at this proof and produce the proof for this equality. Just one by one. That's a good exercise. So maybe just let me conclude. Maybe it's about time to finish. So the motivation for the dipole property is that first it was used. It kind of naturally occurred in the proof of the Hahn-Neumann conjecture. And then when you state it in the analytic terms, it is going to be related to a Tia problem. And it kind of philosophically, I would say, it's not an exact statement, but philosophically, this dipole property is kind of roughly equivalent to the Tia problem. You would expect that when one holds, then the other also should hold. Okay, thank you very much.